Imagine that you can do two surgeries, but you want to know which surgery is better with respect to certain parameters. Imagine that there are three, four drugs out there for a single disease. Which drug is better? How will you understand that? How will you prove that? And the way is statistics, the way is with data. You collect it, the drug effect on quite a few individuals, and you compare. You collect data on how the surgeries are affecting the patients for two different surgeries and compare their behavior and make a decision. My goal today in this talk, in this small discussion, is to tell you the basics of this whole decision making in the medical industry. And this decision making process is backed up by the theoretical ideas, but I will remove the most of the math, but I will focus on the most important idea and the most important concepts just for you in a simple, down to earth language. So I've named this whole thing that care and cure with data for medical professionals, but this talk is also can be understood by people, whether he or she is from statistics background or not statistics background. The basic mathematics that I think is required is understanding a basic of probability and class 12 knowledge of math, or let's say class 10 knowledge of math. So let's see how we can explore. We'll start with a single question from a medical professional and we'll explore it into depth, and we'll dis- go on discovering how to how to answer the question. So let's get started. So first of all, if you're a statistician or a person who has taken the responsibility of understanding via the data, you have to start with a question. This question shouldn't come from you. The question should come from the medical professional. So consider a medical professional to start with a question. That's the purpose. That's the purpose of the data. That's the purpose of doing the analysis. So let's say you have got a wonder drug for rheumatoid arthritis. So the usual remission rate. So rheumatoid arthritis is the autoimmune disease. It's an autoimmune disease, and my mom has it, and it's very painful. So like researchers are trying to understand which drugs works better, and many drugs. So this happened to my mom, that many drugs one of the drugs had a reaction effect on her, on not on my mom but also on my uncle. So he's in hospital right now. So it's kind of I know that this is kind of a really big problem. So imagine that two different kind of drugs, three different kind of drugs. So which works better for different patients? Is to work different. Let's say for one drug, it's affecting a lot of patients. For another, it's affecting not a lot of patients. So are they significantly different? Which one drug to use? This is what statistics does, and let's see how it does it. So we have a wonder drug for rheumatoid arthritis. The usual remission rate for the arthritis is 10 to 60%, but let's say you've got a wonder drug, and this is the data. So let's say you have collected data from patients. Let's say you've taken 100 patients and you've collected data on the remission rate, and you have got the average of the sample is 63. Now the question is, that is 63 a very significant number, or it's just by chance you have taken a better data set? Probably you have a better day. That's the whole purpose of statistics. So exactly the question that what do you mean by significantly is being addressed in this talk. So let's discuss about the whole idea of basic statistical principles and inference. So let's say the unknown true performance of the wonder drug, that actually this is the true performance we do not know. So what we do, we take a small sample out of it, that is a 100 patient data set, that is a known sample, and from that sample we get an idea about the unknown behavior. But remember, with every sample the data changes, hence the prediction also changes. So how to make a decision, informed decision during this, this variability, with this variability in mind? So what we do, to answer that question, what we'll do, we'll explore into the behavior of the data of a sample, and what makes data, how can we extract information out of data in a proper way. So let's say for a sample, we can visualize, let's say for the data set that we have, as I've shown you here, we can club it up into corresponding intervals like this. And let's say you have less than 15% remission rate interval, 15 to 25, 25 to 35, 35 to 45, 45 to 55, and more than 55. And you have goes relative count. And if you plot this data, it looks like this, as you can see on the screen. So for a sample, we can visualize like this. But the shape changes from sample to sample. When the sample changes, the count changes, the relative count changes. Remember, the relative count is total number of count. Okay, let's say in 15, there are 8 people, so we divide by 100 to get 0.08. In 15 to 25, there are 11 people, so divided by 100 to get 0.11. So this is how we count the relative count. So now, this is the basic idea, that the shape changes with the different samples. So what we do now is that observe that there's a basic truth, the basic true behavior of the entire true behavior, unknown behavior that we don't know. Okay, that is denoted by the red line. That is the actual relative count of the remission rate of the true wonder drug. But what we're getting a sample, and hence this shape of this blue colored shape is changing with every single sample point. But remember, we have only one sample point, like one sample of 100 patients. So that's the best we can get. The sample that we have, that's the best we can use to understand the behavior of the actual unknown population. So what does a sample say about the unknown behavior? Observe that the blue curves are the actual, the blue curves are the, the estimated, the sample numbers, and the red curves are the actual curve. So that's the best, that's the best you can say. It's not true. You can see it's not true. For different sample, samples, you will get different estimates. But given the sample you have now, that's the best you can get, right? And it sometimes gives quite a good estimate, right? You can see on the right hand side, gives quite a good estimate. But in this middle one, doesn't give a good estimate. So this is a good estimate. So 0.08 is a good estimate of the actual less than 15, the relative count. The 0.11 is a good estimate from the sample, because that's the best we can have, right? That's the best we can have of the relative count of the remission rate between 15 to 25. So this is what a sample says about the unknown behavior of this entire population, the entire behavior of the wonder drug. Now, to know more about data, to more about the distribution, the behavior of the data, we need to know a few more ideas, and we will explore it by this example. Let's say you have 2 classes, class 1 and class 2. And your question is that, which class performs better? So what you will usually try to do is that you will try to come up with a single number. Let's say there are 2 students, and you understand to which 2 students work, perform better. What you do is that you take the average of all the students in all the subjects, or you take the average of that student in all the subjects, you take the average of the students in all the subject, and you compare them, right? That's the idea. The idea is that to give a single number, because you cannot compare a pair of numbers. You can only compare a single number, okay? You cannot give an order to a 2 points, because there is no order in that 2 points, right, in the space. So you can give an order on a single real number line. So you can know that this point, the positive number is greater than negative number. So there's an order inside that. So a single number, you want to give a single number understanding to a set of a behavior of a data point. And that's where we come up with class and average. Okay, we take the average of the entire class, the marks of all the students of the class, and we tell you that if the class average is greater than like one class is greater than the other, then this class has has better score than the other. Okay, doesn't mean that all students have scored better, but the average is better. So it's a combined behavior is better, right? So now there are certain anomalies, like there can happen that actually the students in one class have have performed bad, but one student, like most of the students have performed bad, but one student have performed really high, so the class average may get higher, right? So observe that in that case we use median, okay, which remove this external outlier cases, and we focus on the most important region. Okay, observe, if you take the median, what is the median? Median of certain numbers is the middle number. Let's say if in 1, 3, 5 and 7 and 9, 5 is the middle number, so 5 is the median of this set, 1, 3, 5, 7, 9. So if you observe in this in this class 1, as you can see below in that line, on that line, that the median is between is 27, but the class average becomes 51, which is greater than the class average of 41 and median 40. So therefore, in this case, you can understand that if we take the average, we get a bad estimate than if we take a median, because it shows you the true behavior of the most of the people of the class. So there are different numbers you can use in different scenarios to understand, to give a single number representative of the entire entire sample or the entire data. That is called a central tendency. Okay, this is what is called a central tendency. Now the question is that, is average enough to measure the performance of two classes? The answer is no. The example is given below. So you can observe that here, if you take this class, the average is 47. This class also average is 47. But you can see this is a lot of variability. Like few people have performed really well, few people have performed really bad. But the class average is turning out to be 47. But here there's a consistency out here, right? And for that, we need something called a measure of variability. The persons who are consistent should be better, right? So therefore, how to measure this consistency? We'll explain it by a beautiful example. Let's say you're playing a dart game. Now your goal is to find the best player out there. How will you find it? Observe that in the first one, in the upper left-hand corner, you will see that here it's the best. You can understand why it's the best, because it's consistent and it's within this, in this red region. In this, it's quite consistent, but it's not within this red region. In the bottom left. In the top right, you can see that the average is around this red region, but it's not consistent. It's not close enough. So the person it's not consistent, right? And in this case, it's the worst case scenario. It's neither consistent, neither it's around the red region, right? So best player is this dart in this upper left hand corner, and the reason is that it's close to the mean. There's a mean is close to the red region, and also the consistency is there. So how to measure this? How to measure how to give a number to the player's performance? If you think about this, you will see that you can give the number in quite a few ways. Observe that what you do is that there's a mean, and if the mean is close towards so first measure is mean, right? The mean should be close towards a red dot. That's where the average comes up. But also, if you take this another quantity, that let's compare the not in the first row case. In the first row case, both the mean are in this red region. Both their means are around this red region. But in the upper right corner, where the variability is more, observe that the distance from their mean, that is denoted by the black lines. If you take the distance from their mean, the distance square of their mean, and sum it up, this upper right corner has much more the variability than the upper left corner, right, where the restriction is it's around small region. So therefore we can compute this, we can measure this consistency by the distance, sum of the distance, or rather the mean of all the distances. You can see on the right hand side the mean of all the distances from its mean, and the more it is, the more variability is and lesser the consistency. Okay, so the inverse of variability is like variability is related to consistency in this way. The more the variability, the lesser the consistency. The lesser the variability, the more the consistency, right? So therefore you can measure the performance of this dart players in this way. Okay, so therefore this tells you the definition of variability, that it can define as the mean of summation of xi minus x bar whole square. That is nothing but the distances from xi from its corresponding mean, which is in the red region. So it's nothing but 1 by n summation of xi minus x bar whole square. You can also take a different distance. We just take the length, not the length square. If you take this distance, it turns out to be 1 by n summation xi minus x bar modulus. But you can ask that why we are not taking xi minus x bar, why you are taking square or mod? Because xi minus x bar, it will turn out to be 0. The reason is that everything will cancel out. There's some positive movement, there's some negative movements, right? And also in 2D, you cannot like find this positive negative. So you need to define by distance. And also, you have to define this sum of the distance. The variability is in terms of distance. There should be some, you should turn it into a positive number. So xi minus x square denotes square of the distance from those two numbers, between those two numbers. Xi minus x bar mod gives you the distance between those two numbers, but xi minus x bar doesn't give the distance. And in fact, there's no notion of distance in that. So therefore, what we'll do, this 1 by n summation xi minus x bar whole square for the data set gives you the idea of standard deviation, the variance. So of course, the average is not enough. So what you define is that root over of this first expression, the first wide algebraic expression, so 1 by n summation xi minus x bar whole square, that gives you the idea of variance. And if you take the square root of it, that's called the standard deviation. So for this class 1, observe that for the same thing, the standard deviation is 10 here and the standard deviation is 28 here. That means more consistent in this class 1 and the less consistent in class 2. So therefore, we using these two parameters, one is average or central tendency and another is measure of variability, you can understand quite a lot of behavior of a set of data. And with that, we will start to explore more about what this unknown population and known sample parameters can say about each other. So observe that therefore you can understand for the actual true population, if we understand the mean and the standard deviation, we can actually know a lot about the population. So the question is that, what can a sample say about this unknown average and standard deviation, which are really great parameters to understand a certain set of data, understand a population? The best estimate we can show mathematically and statistically that are the actual sample mean and the sample averages. Okay, if you take the mean of all these numbers, okay, that you have got, and like mean of all these numbers that you have got here, okay, and the average, mean and average, and the standard deviation, that are the best estimates that you can have for the actual population and actual behavior of the actual wonder drug. So that's the best quality estimate. That's what I mean. So if you have got sample average is 34 and standard deviation is 12, that's the best estimate that we can get as about the population parameter and population parameters. That means population average and population standard deviation. Now the question is that. Now the next question is that, let's say we take 4 different samples. Okay, one, we have sample size 100 and we have got the mean 55.5. Now the remission rate. For another sample, the sample size is 45 and we have got 50.5. The third sample, we have got a 10 sample size, but we have got mean 60.4. And for the fourth sample, we have got 1000 sample points, but the mean is 60.3. Now we have to compare with the 60 remission rate, right? The question is that, which one is significant? Like, is 10 sample size with 60.4 really significant? Or is sample size is sample size 100 with mean 55.5? Is it too, does it show you that that it's not 60? Understand that with different sample, the different means will come up. So there's a chance that it can sometimes go over 60.4, it can 60, it can sometimes go below 60. But how much? What is the sweet spot that we can say that, okay, it's valid that actually there's a difference between 60 and that number, because there's a certain chance, there is a certain randomness involved to it. What is that sweet spot? What is the, how we can understand and distinguish between these two things? And that is what the whole statistics is all about, tell you significance, like what is the sweet spot. But the basic idea that I wanted to share via this slide is that the more the data points, like if you get an information about something from a lot of people, that means that is probably much more true, right? So if 1000 people are saying that 1000 data points are saying actually the mean is 60.3, it's much more valid than saying 10 people are saying that the mean is 60.4, right? The more the data, the more is the belief. And you can prove it mathematically too. This is called the limit theorem, the law of large numbers. The more the data, the better is the, the more is it's true. That's the whole idea. So this is the whole idea of studies that we'll be learning in the next few steps, that what is how to find this sweet spot, right? So let's explore. So the question is the following. This we have got a sample remission rate to be 63%. Your hypothesis is that now the goal is you have to compare with 60, right? As you can see. So your hypothesis is that the mean is 60, but I think that mean is greater than 60. So you tell that it's 60 because the small extra bit can actually happen by chance, just happen by chance. But I say no, this small change from 60 to 63 is, like, we have taken a sample, the sample remission rate, the average sample remission rate is 63. So my viewpoint, my argument is that this small change is quite significant since there are 100 patients, a lot of patients out there. But your viewpoint is that it's equal to 60 because the small change actually can happen by chance, right? So if we have these two different viewpoints, how will we justify which one is true? Let's see. So we will explore it like we two are victims, and we will use a judge, a data judge, to tell you, the statistics judge, to tell you which is true, probably. And so let's say your hypothesis is 60 and my hypothesis is greater than 60. So what we do in statistics is very simple. We use the method of contradiction. So we assume that your hypothesis is true. Okay. We assume your hypothesis is true. It's simple. Mean is equal to 60 is a better hypothesis. It's a simple hypothesis to work with. So we assume your hypothesis is true. You have a hypothesis. We call it null hypothesis. We assume it's true. And we have the data from there, which tells you the mean is 63. Right? And we now check your hypothesis and how much the data are coherent with each other. That's a statistical, we'll show it in a much more mathematical way, much more intuitive way, intuitively statistical way. So if it turns out to be coherent, we accept that your hypothesis is true. Whether we cannot reject it, you can say. But if it doesn't turn out to be coherent, we say that the alternate hypothesis, my hypothesis, is actually correct. It is greater than 60. This is the idea of contradiction that statisticians use to prove things in a statistical way. Now, let's take this. So this is a probability distribution. Let's say you're taking out sample from this actual distribution whose mean is 60, right? And you're taking out 3 samples, right? You're taking out samples from this distribution and you're taking out 3 samples, right? Now this is where you need to understand a bit of probability. But imagine there's an underlying population who's, let's say you have an underlying population of people whose height is 60 some parameters, 60 some units, and you're taking out random people out there and you're taking the sample, and here's a 5 point sample, 3 samples are there, okay? In each of them each of them we have 5 points, 5 sample points. Observe that the actual mean is 60, but the sample mean is denoted by blue, can be a bit off. It shouldn't be exactly equal. It cannot be exactly equal, okay? It can be a bit off, always. Sometimes it's greater than, sometimes it's larger. So it can happen by chance. It's actually a bit off, okay, a bit more. Also, the sample, like, it can happen 60.3, it can happen by chance. That's what I mean. Also, if it's too much, probably if it's too much, like if the sample is too much of a difference, probably there's something going on in the actual population, okay? If the sample is too much of a difference, there's something probably going on, okay? And if you have a data point where you see that a lot of people are against something, are telling you something against that, and a lot of people are doing that, probably there's something to worry about, there's something to question, there's something to be curious about. And that's what you have to find. So therefore, too close can be happen by chance, but if it's too far away, that probably there's something to be curious about. Right? Now, what is the sweet spot? What is the sweet spot? Is there a sweet spot? And too much far away gives you 60, too much far away from 60 probably tells you that there's something fishy going on. But too much close away can also happen by chance. So there's a middle point where the sweet spot where things, the phase changes, the idea, the decision changes, and that's what we call the sweet spot. So let's say if you have the sweet spot is 61.4, so till 60 to 61.4 everything can happen by chance, we assume that. But if it's more than 61.4, the mean can be greater than, like, we can tell you that, okay, there's something fishy going on, probably the mean is greater than 60. If the sample mean comes out to be between 60 and 61.4, you will probably get that, okay, I mean, it can happen by chance. But if it's more than 61.4, probably will say, no, there is something fishy going on. Probably the actual population mean is greater than 60. Now, how to determine the 61.4? Or why is it 61.4? How do you determine this specific sweet spot, right? So that's where this idea of, like, the question is, how do you find this sweet spot? The basic idea is that the errors make it up. Okay, so let's say the truth is mean is 60 and other truth is mean is greater than 60, and you reject mean is equal to 60, or you accept mean is equal to 60. Now, if the truth is mean is equal to 60 and you reject mean is equal to 60, with this sweet spot 61.4, right? Let's say S is the sweet spot. If it is greater than S, the sample mean is greater than S, we reject. If the sample mean is greater than S, we reject the fact that the mean is equal to 60. We accept the fact the mean is greater than 60, because it's too much of it's, this cannot happen just by chance. But if it's between 60 and 61.4, we say that, okay, the mean is probably 60. So based on this sweet spot, we make a decision, right? So this truth is, let's say mean is equal to 60 and mean is greater than 60, and based on the sweet spot, this we reject mean is equal to 60 and we accept mean is equal to 60, right? But it can happen that mean is equal to 60 and we reject mean is equal to 60, even though it's on the other hand side, because it can happen by chance. We are very lucky. We are very unlucky, probably. We have got a very good sample. And similarly, it can also happen the mean is greater than 60, but we have got like between 60 and 61.4. In that case, it's also an error. Again, we're unlucky. So since we're unlucky, we call these errors. The first one, when the truth is mean equal to 60 and we reject mean is equal to 60, we call it type 1 error. And the other case where mean is greater than 60, but we accept mean is equal to 60, it's called type 2 error. Now, your goal is to minimize this so that you find that best sweet spot, right? So the goal is to find the sweet spot. Your goal is to minimize it. And to minimize it, we can show you that both the errors cannot be minimized together simultaneously. Why? So let's say you always make the decision, whatever the sample, you always make the decision that the mean is equal to 60. Since you always make the decision mean is equal to 60, when mean is equal to actually 60, and you never reject mean is equal to 60, right? You always accept it. So hence the probability, the probability of that type 1 error is always 0, because you always accepting mean equal to 60, whatever is the outcome. So given that when the truth is mean equal to 60, you are never rejecting it. That means the probability, the error is 0, right? But when mean is equal greater than 60, and you're always accepting mean equal to 60, the probability is so high. It's actually probably 1, always 1, right? So also to take the other case, you always reject mean equal to 60, then it will become 1 and this will become high and this will become 1, right? You always reject mean equal to 60. Whenever mean is equal to 60, you will reject it. So it's high, it's 1, it's 0. So therefore, you can see that it's a two extreme cases and it cannot be minimized together. If you want to minimize 1 to 0, if you want to minimize one error to 0, the other goes high. If you minimize the other to 0, the other 1 to 0, the other goes to high to 1. So therefore, we cannot be minimizing together. We cannot minimize the errors together. So there is a different way to find the sweet spot. So what we do, we fixed this type 1 error at some probability called alpha. Okay, there's a probability of type 1 error. We fix that probability to be alpha. And we chance to be alpha. And we fixing that at that point, we minimize the type 2 error, right? And this alpha is called the level of significance. Now, fixing this alpha is given by the domain knowledge. What is alpha? Alpha is telling you that, let's say alpha is equal to 0.05. It's telling you that 100 times, if you get the 100 times, in the case of true mean is equal to 60, you will reject 5, right? You will reject 5 of them. So it's kind of mean is equal to 60, but you're getting mean greater than 60. That is kind of false positive. But mean is greater than 60, you're getting like the type 2 error is kind of false negative. Okay. So you fix a false positive chance, the probability of false positive to be alpha. That means out of 100 times, you will allow this many amounts of false positive. Okay, that is the alpha. Okay, it can be 5, it can be 1, it can be anything, but it can be 10. So it can be 0.05, 0.01, 0.1, whatever. Usually 0.05. And fixing this false positive, the amount of false positive you can afford to, you minimize an false negative, the chance of false negative, and that gives a sweet spot. I am not going into details how it happens, but this is how we find the sweet spot. So in a single frame, what we do is this, that we assume, like, we have a null hypothesis means equal to 60, we have alternate hypothesis means greater than 60. So we assume the null hypothesis to be true. We fix the type 1 error, the chance of type 1 error to be at alpha, at that level of significance. We fix the false positive to be at alpha, chance of false positive to be at alpha. This is like fixing the amount of false positive we can afford to, and then we minimize the type 2 error. Minimize the type 2 error, we get the sweet spot S. Now, this sample mean, this is called a test statistic. The sample mean we check whether it's greater than S or less than it. That is the sweet spot, right? Just like here, we check whether it's greater than S, that's 61.4. It is greater than S or less than S. So if it's greater than S, we reject the criterion because it's too much to accept as a simple chance. If it's less than or equal to X, we accept the criteria. Like, we cannot reject it. So if it's greater than S, we reject the null hypothesis, that is it's equal to 60. We accept it that it's mean greater than 60. If we cannot reject it, if the sample mean is less than or equal to X, we cannot reject it, the null hypothesis. Okay, understand, it's more than 60, so we cannot have enough data to reject it. That's the basic idea. It's not exactly 60. So that's the basic idea. That's the whole point. That this is the whole point, the whole idea, the whole steps. This single frame gives the entire steps to find out the decision, to do the decision making based on the sample. So these are the red things, the red marks things are the important definitions that are, to understand the testing a hypothesis. So now with this, another concept comes, that is called the p-value. So the p-value is this, that let's say your mean is like 60. Now when your mean is between 60 and 61.4, the sweet spot, you cannot reject the null hypothesis, right? But when it's more than 61.4, that is sweet spot, you reject the null hypothesis, mean greater than 60. Now, how do you define the p-value? So let's take this number, okay? Let's take the sweet spot. So this right-hand side, nothing but the area under the curve is nothing but the probability that the sample mean is greater than this point, the black point, that is the sweet spot, that is 61.4. That means in this region, what do? In this region, you reject the null hypothesis, right? So now we are assuming the distribution to be the true null hypothesis, that is 60, the mean is 60, we are assuming it. And this black area gives you the probability that given it's true, we're actually rejecting it, the probability of it's being rejecting it. So therefore, this is nothing but the type 1, the alpha, okay? This is nothing but the alpha. The actual red curve is the actual curve. Given the true value, that the mean is 60, this black area is nothing but the probability the sample mean is greater than or equal to 61.4. That is sweet spot. That is nothing but we're rejecting in this area. The probability that we're rejecting given that the mean is 60. And that is nothing but the alpha, the type 1 error. Right? Now let's take a number between this in this gray region, in this region where we do not reject. Observe that at that point, in that region, if you take a point in that region, the blue curve, the blue area is actually nothing but the probability is greater than that point, 60.7. Let's say we have got 60.7, the sample, the sample mean. So what do I mean by sample mean? This is nothing but the distribution of the sample mean, okay? This is nothing but the distribution of the sample mean. We assume that the mean is 60. So this is the actual distribution of the sample mean, assuming the mean is 60. This black region tells you the type 1 error, alpha. Now, if you take any point between this, in this region where we cannot reject null hypothesis, this is the blue region, right? Observe that is greater than or equal to alpha, because it's this portion plus the black region. You can imagine it geometrically, right? And if you take a point where in the red region, the rejection region, it's less than or equal to alpha, right? Let's say you take the probability less than or equal to black area, right? That is equal to alpha, less than or equal to this point is 62.3. We take the probability that the sample mean is greater than equal. We have got a sample mean to be greater than equal to 62.3. We have got less than equal to alpha. Therefore, p-value is nothing but if the p-value is greater than equal to alpha, the type 1 error, that's the level of significance. That means we cannot reject it. Okay, this is into the gray region. If it's more than the the sweet spot, that means it's the red region. That means it's less than equal to the alpha. The p-value is less than equal to alpha. That means it's the red region. That means we have to reject it. So you can actually, this rejection criteria is equivalent to saying the sample mean greater than S is equivalent to saying the p-value is less than alpha, right? It's less than alpha. It's like a smaller region, the smaller area. If the sample mean is less than equal to S, the p-value is greater than equal to alpha. So you can also make decision based on p-value. You just count the p-value, which is done in the calculators right nowadays. If we compute the p-value and the p-value is less than alpha, then we reject the null hypothesis. If p-value is greater than equal to alpha, we accept the null hypothesis. That's the basic idea. Okay, so this is how you can transfer this rejection region. Rejection criteria is equivalent to the p-value, and that's what the whole idea is all about. The whole concept is all about. I hope you like this explanation. I hope it was not too mathematical. I've used the concepts of probability, I know, but I hope you understood. I have tried my best to make it simple, make it crisp, make it just share the fundamentals to you via important medical example. I hope you enjoyed it. And if you enjoyed it, do give a like, do share it with the people whom it can help, and be curious. And thank you for your time again. Thank you for your attention, and I will see you in the next video. Stay tuned and stay blessed. Have a great day ahead. Bye bye.